Hey there, this is Horner, and these are the notes on Chapter 13. This talks a lot about temperature and some other related items. The next unit will be on heat, and so we'll go through the temperature first, and then we'll look at heat. And just as a side note, temperature and heat are not the same, so you'll see that as we go through. The definition of temperature is based really on what we call thermal equilibrium. So you have a couple of different objects and they will exchange energy, and the energy will always go from an area of high temperature, so you got to remember this, to an area of low temperature. So those temperatures will start to get closer together, and once the temperatures are equal, there's no longer a net flow. Okay, so there's still flow in and out, so we still have flow in and out, but because those two are equal, we say there's no net flow. So temperature is really just a quantity that determines when a couple of different objects are in thermal equilibrium. The energy that flows between a couple of different objects is called heat. So heat is not the same thing as temperature. Temperature is just a measure of the amount of energy that is contained within a certain object. And so we can kind of think about it that way. And heat is the flow of energy between a couple of different objects that have a temperature difference. So if we can have heat flowing from between two objects or a couple different systems, we say that those two things are in thermal contact. Kind of like if you put your hand on a hot stove, that would be one example, or if you put your hand on a block of ice, same type of thing. So to measure the temperature, we can use a thermometer. We say that that's in thermal contact, and we wait till the two things get into equilibrium with each other. So when you put a thermometer in your mouth, it is cooler than your mouth is, and so when they come to equilibrium, you can find out what the temperature of your body is. And this relies on what we call the Zeroth Law of thermodynamics. What is the Zeroth Law of thermodynamics, you ask? It is basically just when you have two objects that are in a thermal equilibrium with a third one, then the two are basically in thermal equilibrium with one another. Temperature scales, kind of an interesting story here. The one that we use most often in physics is called the Kelvin. And it is not a degree scale. It is just an absolute scale. So 0 Kelvin represents what we call absolute zero. But if you want to convert from Kelvin to any other temperature, we can take the Kelvin temperature. So this T without anything below it is what we call the absolute temperature, or the Kelvin temperature. And we just subtract 273.15. That gives us Celsius. If you have Fahrenheit and need to go to Celsius, you just subtract 32, divide by 1.8. If you want Fahrenheit and have Celsius, you multiply by 1.8, then add 32. And if you want Fahrenheit, you can take Celsius and multiply by 1.8. If you want the change in temperature. So just a little background on temperature scales. Core body temperature is about 37 degrees Celsius or 98.6 Fahrenheit. Room temperature is about 20 or so, which is about 68 degrees. Melting point is 0 or 32, and then steam or boiling point is 100 and 212. So just things you kind of already knew. Just some reference temperatures, kind of what they are. Intergalactic space is pretty cold. It's about 3. Absolute zero is 0. The lowest transient temperature, so what we've tried to get to, we've not hit absolute zero, but we've come very close. So 0.000000001 would be the lowest temperature that we've ever seen. Some reference temperatures, just when water boils, campfire, gold melts, the center of the Earth, center of the Sun, interior of a neutron star, so pretty hot temperatures there. For example, 13.1, we have a friend suffering from the flu. They say that her body temperature is 38.6, but because we live in the United States, we use the English system, so let's convert this to first Kelvin, so we can do it in the physics world, and then we can do it in the United States, which is degrees Fahrenheit. So temperature in Kelvin here should be equal to 38.6. That's degrees Celsius, but that is a temperature change plus 273.15. And when you add the two together, you get 311.8 Kelvin. So pretty easy. For Fahrenheit, we're just going to say that the change in temperature in Fahrenheit is equal to 38.6 degrees Celsius times that 1.8 degrees Fahrenheit for every degree Celsius. and that gives us a temperature change of 69.5 degrees Fahrenheit. And then all I have to do is add 32 to that in order to get my total temperature. So her fever is 101.5 degrees Fahrenheit, enough to keep her away from school and away from others since she's got the flu. Next one is linear expansion. So if you heat up a wire, a rod, or a pipe, that pipe will lengthen, or that wire will lengthen, or that rod will lengthen. So the equation that we're going to use for that is the change in the length over the original length is equal to, and then we have alpha, and alpha is what we call the linear coefficient of expansion, or it's a proportionality, it's a coefficient of linear expansion. So we take that times temperature, the change in temperature, and that'll tell us how much longer that will get. If we look at the next slide, you're going to see some coefficients of linear expansion. The bigger the number, the more it expands upon freezing, so no surprise. Ice, if you take a can of pop and you put it in the freezer, it will explode. And then we always use Pyrex glass because it does not expand much when you heat it, which is good, especially in a chemistry lab. There's another glass called Vicor glass. It's got an even smaller amount of expansion, so you can really heat it up pretty well. Obviously, you see brick doesn't expand much, hence why we put it on the outside of homes. Lead, on the other hand, expands pretty quickly, so does aluminum. You'll see a lot of these metals do this pretty well. Concrete or cement will expand at a factor of about 12 times 10 to the negative 6. So just some coefficients. So over a limited temperature range, we will get kind of this straight line curve. You will see that this is actually the curve that you get for when a metal expands. And so the thing that we do is we just look at over just a smaller temperature range here. And if we do that, that's where we get that coefficient A. So that's just finding that coefficient is plotting these temperatures and then finding somewhere along there where we can get kind of a nice best fit tangent straight line. Next problem here, we've got two metal rods. One is aluminum and one is brass. Each are clamped at one end. And so what they want us to do is, it says at 0 degrees Celsius the rods are 50 centimeters long, so they're each the same amount. And they're separated by this 0.024 centimeters. They want to know at what temperature will those rods just come into contact, so we can assume that the base of the rods are clamped and they undergo a negligible small thermal expansion. So some things that we know the length of each one is 50. We know the temperature starting at 0 degrees. We had to look up the coefficient of linear expansion for each one of the two metals, and we have that now. And we know the requirement is the change in the brass and the change in length of aluminum together need to be equal to 0.024. So we're going to find out what that final temperature is by taking that original plus that change in temperature. So to do that, here's the change in the brass, here's the change in the aluminum, and we want to just basically add those two together. So we can say that the change in the brass plus the change in length of that aluminum should be equal to 0.024 centimeters. And if you add these two things together, notice that the temperature change and the original lengths are the same. So we can just combine the alphas. So the alpha for brass plus the alpha for aluminum. Then we can multiply that times the change in temperature times the original length, and that should be equal to 0.024 centimeters. Let's rearrange this for the change in temperature. So our change in temperature here is equal to 0.024, and then we're going to divide that by our alpha for brass plus our alpha for aluminum, which is also multiplied by the original length of both bars. This is equal to 0.024 on the top, and then on the bottom we're going to have 19 times 10 to the negative 6. That's the alpha for brass, plus 23 times 10 to the negative 6. That's the alpha for aluminum. Had to look both of those up, and we can multiply that by 50 centimeters. And that's equal to about 11.4 degrees Celsius. And so now we need to go through and we're going to take our final temperature. That's equal to our original temperature plus the change in temperature we just found. Nice thing is our original temperature was 0, so we can add that to 11.4 degrees Celsius, and we end up then with an 11.4 degrees Celsius final temperature. So we're just going to heat it up to 11.4, and those two rods should just touch. So not too bad of a problem there. That's 13.2. So now we can kind of think about something called differential expansion. Inside of your, if you have a thermostat at home for your home or for your apartment or in your dorm room, one of the things that we do is we make a bimetallic strip. So it's got brass on one side and has steel on the other. And when it's cold, the brass side will expand and contract quickly based upon the steel. So when this contracts very quickly, you'll notice it goes kind of curves in to the left. When it expands very quickly, then it pushes that steel over to the right. So this we can use that, and you can turn on and off your heat and your air conditioning with that bimetallic strip, which is kind of a cool thing. Area expansion, so we did linear expansion. Now we can think about maybe a cookie sheet in the oven. That cookie sheet in the oven might start out like this, and then the red is going to represent how much bigger it gets. It won't get that much bigger, but it might get a little bit bigger. So if it does, because it's expanding both this way and this way, notice that the cookie sheet does get a little bit bigger. So for small temperature changes, the area of any flat surface does change in proportion to the temperature change. So here we're going to have 2 times alpha, and then we can also do volume expansion, where maybe I've got some sort of bolt, and that bolt will expand in this direction, it will expand in this direction, and it will expand towards us. So there are 3 dimensions it expands in. We call that volume expansion. And then we use beta, and beta is really just 3 times alpha. So because each one of these is expanding in a different direction, this one in the x, this one in the y, and this one in the z, we can just take 3 times alpha, and 3 times alpha is going to give us our coefficient of volume expansion, which is what we call beta. So pretty easy concept to do. If I have a hollow cavity in a solid, for example, if I have a block and it's got a circle on the inside, when this whole thing expands, it will expand outward. Okay, it will not expand inward. So the block will get bigger, and then the circle will also get bigger. The circle does not get smaller. That's a pretty common misconception. So if you think about a can, the steel wall of the can does not expand inward. That whole can will get bigger. So if you thought about just an aluminum can, you heat it up and it will get bigger outwards, not inwards. We have a hollow copper cylinder here. It's filled to the brim with water at 20 degrees Celsius. They say if the water in the container are heated to a temperature of 91 degrees, what percentage of the water spills over the top of the container? And that's because the water will expand quicker than the can will. We know the initial copper cylinder interior volume and the initial water volume are the same, so they're both VO. The initial temperature is 20, the final temperature is 91 degrees Celsius, so we have a temperature change here of 71. We looked up the value for alpha for copper. It's about 16 times 10 to the negative 6, and then beta for water is 207 times 10 to the negative 6. So to really find the change in volume as a percentage of the original volume, we're just going to subtract the change in volume of both of these objects as they're heated. So let's go through and do that. We already know that the change in volume of the copper is the beta times the delta T times the original volume of the copper, and then we have the beta of copper is going to be equal to 3 times the alpha of copper because it's expanding in all 3 dimensions. The delta V for water is equal to the beta for water, and we take that times the change in temperature times the original volume. So now what we can do is we can say the change in volume of the water minus the change in volume of the copper, and this is because we know the volume of the water will expand more than the copper will, is equal to the beta of the water times the change in temperature times the original volume minus the beta of the copper times the change in temperature times the original volume. So now we can factor out the betas, so beta of water minus the beta of copper, and that's because the temperature change and the original volume are the same. This is going to be equal to, I'm going to move this all the way over, so 207 times 10 to the negative 6th degrees Celsius to the negative 1, so it will expand this much per degree Celsius minus 3 times 16, because we've got 3 times the alpha for copper, times 10 to the negative 6th. This is degrees Celsius to the negative 1 also. We're going to multiply that times 71 degrees Celsius, and we're going to multiply that times the original volume. So we find out that here it's about 0.011 times the original volume, and that would be 1.1% of the water will spill out. And that is your answer. So that was example 13.3. Let's go ahead and take a look at the next section. This is the last section for chapter 13. And this one just says the number of molecules. This is looking at the molecular picture of a gas. So the number of molecules of a gas per unit volume is called a number density. So in SI units, we just do this in the number of molecules per cubic meter, or meter negative 3. So that's read per cubic meter. So if I have a gas that has a total mass of m and it occupies volume v, and each molecule has a mass m, then the number of gas molecules is just m over that little m. And the average number density can then be m over m times v, which is equal to rho, which is our density, over that m that we said for the molecular mass, where density is just mass per unit volume. So that's essentially what we've done. Let's go ahead and see how we can use this. So it's common to express the amount of a substance in terms of moles. So if you've been through chemistry, you kind of know what's going on here. It's based on the carbon unit, which has got exactly 12 grams. So that's carbon 12. And we use something called Avogadro's number, 6.022 times 10 to the 23rd units per mole. So the number of moles here is just the total number of divided by the number per mole. So let's go ahead and take a look at molecular mass and molar mass. The mass of a molecule is usually expressed in something other than kilograms because it's really small in kilograms, as you see here. It's about 1.66 times 10 to the negative 27th. So instead we're going to use the symbol mu, and that is an atomic mass unit. So when we say one atom of carbon 12 has a mass of 12 atomic mass units exactly, so we've based everything on carbon. Instead of molar mass, tables commonly will give us the molar mass, and that's basically just the substance per mole. The atomic mass unit is chosen so that that molecule U is the same as the molar mass. So for example, O2 has got 32 grams per mole, and the mass of one molecule is also 32 U. Atomic mass units is what we call that. So now we've got a helium balloon, and that helium balloon contains about 0.10 cubic meters of 0.4 moles of helium gas. They want us to find the number of atoms, the number density and the mass density for this helium balloon and the helium on the inside, and then they want us to estimate what the average distance is between those helium atoms. So for our first one here, what we're going to do is we're going to say N is equal to the number times Na. So this is going to be equal to 0.4 moles. So N here is the number of moles. And then we're going to do Avogadro number, and that is 6.022 times 10 to the 23rd atoms per mole. That's Avogadro's number. And that gives us 2.4 times 10 to the 23rd atoms. So now we know how many atoms there are. Let's find out how many atoms there are per unit volume. So that'd be 2.4 times 10 to the 23rd atoms divided by our 0.01 cubic meters. So that gives us 2.4 times 10 to the 25th atoms per, atoms, I want to do atoms before I do my slash, atoms per cubic meter. And then here our molar mass is equal to 4 atomic mass units times 1.66 times 10 to the negative 27th kilograms per atomic mass unit. And so that tells us that there are 6.64 times 10 to the negative 27th kilograms. So our density here is equal to mass per unit volume, which is equal to our molar mass times N over our volume. So here we're going to do our 6.64 times 10 to the negative 27th kilograms times 2.4, so our N over V we said was 2.4 times 10 to the 25th atoms per cubic meter, and we get 0.16 kilograms per cubic meter. So that's our final answer for that part. So we said it was about 2.4 times 10 to the 23rd atoms, 2.4 times 10 to the 25th atoms per cubic meter. The molar mass here was 6.64 times 10 to the negative 27th. That's just because we know that helium is 4 over 2. So it's got a mass of 4. And then we use that to find out what the density is, and it's about 0.16 kilograms per cubic meter. That's for part A. Let's go ahead and look at part B. They wanted to find the distance between the atoms. So to do that, we're going to say that we have that V over N number again. That's equal to 1 over N over V, which we found earlier. And that's equal to 1 over 2.4 times 10 to the 25th. And that, remember, was atoms per cubic meter. And so this will give us 4.2 times 10 to the negative 26 cubic meters for every atom. So we've just flipped it is all we've done. We know that V over N is equal to 4/3 pi r cubed. And so that's approximately equal to 4r cubed, and that's because pi is really close to 3. I know it's kind of a little bit further off than that, but we can make that assumption. So here we want to find out, we've got V over N is equal to 4r cubed. They want us to find the radius between the two, so we're looking for r here, so we need to solve this for r. If I want to solve it for r, I know r cubed is equal to V over 4n. Now I need to do the cube root of both sides, so this would be r is equal to the cube root of V, I need to make that better, there we go, over 4n. And if you plug all your numbers in, you get about 2.2 times 10 to the negative 9th meters, which is about 2.2 nanometers. That would be the radius. Now if I want the distance between the two, instead of the radius, distance, the diameter would just be 2 times r, and so that'd be about 4 nanometers or so. And that is the end of the lecture for Chapter 13.